1.5, we're going to be talking about complex numbers. So don't shake your head. Don't mute me out. Stick with me because complex numbers are going to help us in order to solve problems that we typically cannot solve. In order to learn about complex numbers, we need to learn about something called the imaginary unit I. Now, I know some of you think that algebra is crazy. It's crazy when it added in letters. It's crazy when you start solving for x. Why are we always solving for x? And now I'm about to talk about imaginary, but stick with me. Let me see if I can get you there. We've learned that some quadratic equations have no real solutions. For instance, the quadratic equation x squared plus 1 equals 0 has no real solution because there's no real number x that can be squared to produce negative 1. You can see if I took x squared plus 1 equal to 0, solve this out, that gives me x squared equal to negative 1, and x equal to the square root of negative 1. So what mathematicians did is said, I'm not satisfied with that. I'm not satisfied with having no answer for a problem. And so they worked with some different stuff and they figured something out. They figured out that the square root of negative 1 can actually help them out. Now, if you go to your calculator and type in square root of negative 1, you're going to get error. Okay? And that's because this is an imaginary unit. Now, it's not like the imaginary friend that goes away. This is just something that's going to help us solve and kind of expand our knowledge of math. So, welcome to college. Welcome to college algebra. We're going to learn something new. To overcome this deficiency, mathematicians created an expanded system of numbers using the imaginary unit I. So, what you need to know about the imaginary unit I is that I squared is equal to negative 1 and I is equal to negative 1. This is called your imaginary unit, and this is the main one that we're going to be using for most of these problems. I squared is going to be equal to negative 1. So I would definitely jot that down in your notes. You'll see some paragraphs written through here. This is just to help you out as we go through the notes. But important things are all of these problems work out, but especially in this section, this diamond of a piece right here. I squared is equal to negative 1 and I is equal to the square root of 1. So by adding real numbers to real multiples of this imaginary unit, the set of complex numbers is attained. And what that means is we're going to begin to work with things called complex numbers. A complex number written in standard form is a plus bi. That's very important because there's going to be several problems that tell you to write in standard form. That means write your real part first and your imaginary part next. This is known as your real, and this is known as your imaginary part. You can see it also has that I on it as well. And so many times there's going to be some problems that you're going to work and it'll say write in standard form, and it may be just simply as making it look like a plus bi. Or it may take it a step further and have you actually do an operation on it. We'll get to that in just a minute. So we're going to take something and we're going to figure out how is the square root of negative 9 plus negative 5, how is it equal to negative 5 plus 3i? This is because if you take negative 5, this is your real part, and you add to the square root of negative 9. The fact that you have a negative under your square root keys off that you're going to end up with something imaginary. So you can see we're going to leave the negative 5 where it is. To kind of show you how this works, I'm going to break off this negative 1. See how we have a negative 1 under here? We learned that I is equal to the square root of negative 1. And so then I work with that as being the I part. And I can see that 9 is the same as 3 squared. So if I do a square root of 3 squared, I get 3. Square root of negative 1, again, that's still my I. And negative 5 is just going along for the ride. So I get a final answer of negative 5 plus 3i. Again, the 3 was the square root of 9. The I was the negative 1. Remember, 9 times negative 1 is negative 9. So anytime you have a negative in their square root, that's going to end up being your I part. And then you square root the 9 or whatever number you had underneath there. In the standard form a plus bi, what we just discussed, the real number is a. I mentioned that, called the real part of the complex number, a plus bi. And the number bi, where b is a real number, is called the imaginary part. Now it may sound really confusing because we just said b was a real number? Well, that just means b is a number like we're used to working with, and now it has an I attached to it. And so you've got the definition of a complex number. If a and b are real numbers, the number a plus bi is a complex number and is said to be written in standard form. If b equals 0, the number a plus bi is equal to a. If b does not equal 0, the number a plus bi is called an imaginary number. A number of the form bi, where b does not equal 0, is called a pure imaginary number. So there's just kind of some vocabulary to go along with that. So now that we've learned about standard form, we're going to be working with operations of complex numbers. And remember, your complex numbers are those a plus bi. So we're going to look at adding, subtracting, and multiplying with these. To add or subtract two complex numbers, you add or subtract the reals and imaginary parts of the numbers separately. So by definition, they look at a plus bi plus c plus di, written in standard form, and their sum or difference as follows. So notice they take the real part a and the real part c and add it together. Then they take the imaginary part bi and the imaginary part di and they add the b and d together and stick an I on it. Same thing is true for difference. So you're going to be adding the real part, in this case subtracting the real parts a minus c, and put your number. And then you're going to be taking the imaginary parts bi minus the other imaginary part to do b minus d, and again attach your I to it. That may sound like mumbo jumbo, but you can always rewind, replay it, and now let's try an example. So first thing we're going to work with is adding. And so when you're adding this together, I'm going to use some colors to help us out. You'll notice that my real part is the 4 and the 1. So I'm going to say 4 plus 1, that gives me a 5. Plus, then I'm going to take my imaginary part, 7i and negative 6i, and I'm going to add those two together. 7 and negative 6 gives me a positive 1i. So I can either write 5 plus 1i, or I could just write 5 plus I. Now that's all I'm going to do. I'm going to slap a box around and say, teacher, I'm done. Look at what I did. There's not a whole lot of work to these because you're just adding reals and then add imaginary. But please do not take it further and say, oh look, that says mo. I'm not even going to say the words. Don't go any further. Your final answer will be in standard form. Your real part listed first and your imaginary part listed second. So please do not overwork the problem. As always, if you get stuck, you work the problem, I think I did it right, teacher. Either take a picture of what you did, email it to me, or let me know which one you're working on in WebAssign. So subtraction is going to work the same way. And what I actually do is I really like addition problems over subtraction. And so what I'm going to do is I'm going to take this negative and I'm going to distribute it throughout this back parentheses. And so if I make this into a positive, I can now distribute a negative throughout here. So now I'm working with an addition problem. Again, I'm going to add my real parts. 1 and negative 4 gives me negative 3. Plus 2i and negative 2i, that's 0i. Now there's no reason to write 0i because 0 times I would just be 0. So this just has a final answer of negative 3. So when you're working with a difference problem, I would distribute the negative and just keep working with your addition. Let's take it up a notch. Now in this problem I have multiple things going on, but the same kind of foundation of this is true. Add your real parts, add your imaginary parts. So the first thing I'm going to do is get rid of these minus signs. And so I'm going to distribute this negative, which just changes the signs throughout this parentheses. And you'll notice that I stopped at the 3i because that was the end of my parentheses. And then this negative, I'm going to change to a positive and again distribute my negative throughout. So now when I'm looking at this, I'm going to look at my real parts, which is a positive 2 and a negative 2, so it gives me 0. And then I'm going to look at my imaginary parts. So I have a 3i and a negative 3i, so that gives me 0. And then a negative 5i, which gives me a negative 5i. So in this case, my final answer would just be negative 5i. There's no reason for me to write a 0 because that does not change the problem. Now in part D, I'm going to do the same thing. I'm going to get rid of my minus sign that's in front of my parentheses. So I'm going to change it to a plus, but if I do that, I have to change the stuff that comes after it in the parentheses. Now I'm going to add my real parts. So that's a 3. I'm just combining like terms here. And a 4, that's 7. and then a negative 7, so it gives me a 0. And then I'm going to do a 2i, a negative, there's like a 1 here, so 2 minus 1, that's a 1. And a negative I, so 1 minus 1, that's 0. So now I have a plus 0i. So in this case, the answer is just 0. So that was kind of interesting here that we would look at 2 of those problems. But again, adding or subtracting, distribute your negatives so you're only working with addition, and then you're just combining like terms. Combine your reals and combine your imaginaries. Now you're working with multiplication, it's still going to be like you're used to working with multiplication. Just pay attention to your eyes, and we might have to do a little substitution to simplify it out. So in part A, I'm just going to distribute the 4 into the parentheses like you're used to doing. So I'm going to say 4 times negative 2 to give me negative 8, and 4 times 3i to give me a positive 12i. Now you can see that I'm done once I work with this one because I've got my real part and I've got my imaginary part, and it's written in standard form. Now let's step it up a notch and look at B. Now in B, you can notice that I have a binomial times a binomial, or in this case really a complex number times a complex number. And so what we're going to have to do is we're going to FOIL or distribute this out. So I'm going to say 2 times 4 to give me 8, and 2 times 3i to give me positive 6i. So I do 2 times 3 and then leave the I attached. And then I'm going to do negative 1 times 4 to give me negative 4i, and negative 1, negative I times 3i, and that gives me negative 3i squared. Now the reason that this happens is because say you were given the same problem, you were working with x's, something that you're used to doing. So maybe I had 2 minus x, 4 plus 3x. So the 2 distributes, the 2 distributes like you're used to. So 8 plus 6x, similar to our 8 plus 6i. But this negative x times 4, that gives me the negative 4x. Negative x times 3x is a negative 3x squared. So your x times x results in an x squared. So the same is going to be true with I times I to give you an I squared. So very important, this goes back to previous slide where we looked at and we said, you know what, I is equal to the square root of negative 1, and we've used that, but I squared is equal to negative 1. This is super important when working with multiplication. We're going to take the fact that I squared is equal to negative 1 and we're going to plug it into this problem. So then I'm working with 8 plus 6i minus 4i, and I'll simplify that up in a minute, minus 3 times negative 1. Simplify this up and I get 8. 6i and negative 4i is a positive 2i, and negative 3 times negative 1 is a positive 3. So you can see when I multiply a complex number times a complex number, I had to go back and remember some of the foundations of complex, substitute back in, and I end up with another real part that I can add together to my 8. So the final answer of this would be 11 plus 2i. Let's try it again. So in this case, I'm multiplying together a complex number and a complex number. But this one's kind of unique. Let's kind of see how this one works out. So again, I'm going to distribute or FOIL, whichever you're most comfortable with me saying, 3 times 3 to give me 9, 3 times negative 2i to give me negative 6i. Now distribute the 2i times 3 to give me positive 6i, and 2i times negative 2i to give me negative 4i squared. I'm going to go ahead and combine these i's together here, and that gives me 9. Negative 6 and positive 6, they actually cancel each other, minus 4i squared. And again, remember your foundations of imaginary, I squared is equal to negative 1. Plug that in for this I squared. So that I have 9 minus 4 times negative 1. Multiply these together. Remember, order of operation, you multiply before you add. So this gives me 9. Negative 4 times negative 1 is a positive 4, so 9 plus 4 gives me 13. Now, how did this happen? I started with two complex numbers, and now I've ended up with a real number. Where'd the imaginary go? So that's kind of the neat part of what we're working with. Is Sometimes when you multiply, you'll notice we had 3 plus 2i times 3 minus 2i. So the positive and the negative, something happened. It ended up with no imaginaries. Let's see what happens when we do something times itself. Now remember, 3 plus 2i, that does not mean, oh look, let me square it up. 9 plus 4i squared. Don't you dare do that. It means 3 plus 2i times 3 plus 2i. Now if you do this over here in the blue, I'm going to know who you are, and someone's going to do that. So please don't do that to me. 3 plus 2i times 3 plus 2i. So I'm going to distribute the 3. And that gives me 9 plus 6i. Distribute the 2i. That gives me positive 6i, positive 4i squared. I'm going to combine like terms. That gives me 9 plus 12i plus 4i squared. And then plug in, remember, I squared is equal to negative 1. Hopefully the more we write that and the more we say that, we'll remember it. So I'm going to plug a negative 1 in right here. 9 plus 12i minus 4. 4 times negative 1 makes a negative 4. If you like, I can say plus negative 4, same thing. Add my real parts together, and that gives me a 5 plus 12i. So you can see in the previous problem, when I had a positive and a negative, the imaginary part went away, but when I have something times itself, I still end up with a complex number. The imaginary part did not disappear on this one. That's going to lead us into our next discussion, and that's going to be of complex conjugates. Keyword, know what this word means. It's going to come to haunt you on a test one day. So complex conjugate, that's not just one of the words that you throw out at the dinner table to show people that you're learning a whole lot in college. This is actually something that's going to benefit us. It says, notice in example 2c, that c that we just did earlier, that the product of two complex numbers can be a real number. I'm referencing that problem that said 3 plus 2i times 3 minus 2i, and we got just a real part. We didn't get an imaginary part. Okay? So this occurs with pairs of complex numbers of the form a plus bi and a minus bi. See, like we have here? These are called complex conjugates of each other. And the reason this works out is if you take a positive complex number and it's negative, when you multiply them together, you end up with your insides canceling out like it did in our problem. You plug in for your I squared, like we did, and you end up with just a squared plus b squared, so a real part. So if we work another problem such as this where you have complex conjugates, let's see if it happens again. So I'm going to take 9 and distribute it to the next parentheses, 9 times 9 and 9 times negative 2. So this gives me 81 minus 18i. Now again, I'm going to distribute the 2i into the second parentheses. So 2i times 9, it gives me a positive 18i. 2i times negative 2i gives me a negative 4i squared. Combine like terms, you'll notice that the negative 18i and positive 18i, those cancel. And so I'm left with 81 minus 4i squared. So just as we predicted, the inside two terms cancel, and I have 81 minus 4i squared. And remember, I squared equals negative 1. So now I keep working this out, and this gives me 81 minus 4 times negative 1. Negative 1 times negative 4, that gives me a positive 4 plus 81, which yields an 85. Now you will have to be able to work on these, not only in web assignment, but also in future assignments, assignments that are worth lots of points, such as maybe an exam. So make sure you know how to work with a complex number. Now, even a question may even say, given the following complex number, 9 plus 2i, what is the complex conjugate? So part A, I might have to say 9 minus 2i, and that's it. And then what is the product of the complex number and its conjugate, meaning work all this out, and so my answer might be 85. So this is a couple questions that can be asked about this stuff. Now on the last slide, I'm going to kind of point and underline as I go, but I did a lot of typing on this one. This is writing a quotient of complex numbers in standard form. So when we go to divide, that operation we haven't looked at yet. And so what you're going to do, given the problem 2 plus 3i equal to 4 over 4 minus 2i, what you have to do is you have to rationalize out the denominator, meaning you're going to multiply the numerator and denominator by the complex conjugate of the denominator. So what you do is you look at your bottom piece, and in our case we have 4 minus 2i, and we multiply the whole problem by its conjugate, which in our case is 4 plus 2i. Now if I'm going to multiply by the complex conjugate on bottom, that means I'm going to end up with a real number, because that's how complex conjugates work. But if I do it on bottom, I have to do it on top in order not to change the problem, and you'll see that this is just a big old 1. So multiplying by 1 does not change my problem, but it's a special one that's going to get rid of my imaginary number on bottom. So on top, you can see that we FOILed it out to get here. We did 2 times 4, and we did 2 times 2i, 3i times 4, 3i times 2i. On bottom, we FOILed it out. My middle term disappeared. I plugged in for I squared. I combined like terms on top. On top, we end up with 2 plus 16i, and on bottom, we end up with 20. Now, the whole point of that is the fact that I can now simplify this out. I can come over here to the side, and I can say 2 over 20 plus 16i over 20. Reduce my fractions down, and that's how I got this number right here. And again, it's written in standard form. So if you're working with a division problem, what you have to do is multiply by a big old 1. Our big old blue 1 in this case was 4 plus 2i, which is the complex conjugate of your denominator. What this does is just create a denominator that's just a real part, and then you can divide your real and imaginary number by that and simplify down. So I hope this helps with complex numbers. As always, let me know if you need any additional help.